Hey class, I had a patient cancel on me, so I'm going to try to bang out this anatomy and physiology lecture, and then we will be all wrapped up with Unit 1, 1/5 of the way done with class already, if you can believe it or not. So this last little mini lecture, as you know, will be about 20 minutes. We're going to be talking about anatomy and physiology of the auditory system. But before we do that, I want to hold up a very important chart that I made up in preparation for this lecture. Through this chart, you're going to see the various designations of how we can sort of categorize the auditory system. Okay, so across the top there, you see outer ear, middle ear, inner ear, and then central auditory pathway. We don't really call it the central ear, but central auditory pathway. Okay, now in pen, between inner and central, you see what's written CNV111. That stands for cranial nerve number 8. Those of you who are well versed in anatomy probably know that there are 12 cranial nerves that innervate various aspects of our senses and also our musculoskeletal system. Cranial nerve number 8 specifically is the vestibulo cochlear nerve. Let me write that out. Vestibulo cochlear. Okay. Vestibulo-cochlear. That means that it innervates the organs of balance, vestibulo, and hearing, cochlear, okay? We have nerve endings coming from the 5 organs of balance, the 3 semicircular canals, the utricle and the saccule, that make up the vestibular branch of this cranial nerve, and nerve endings coming from the cochlea, the organ of hearing, that make up the cochlear part of this branch. That cranial nerve connects the inner ear to the central auditory pathway. Now, the reason why that's in pen is because cranial nerve number 8 kind of enjoys a unique, it's not really part of the peripheral auditory system, but it's not really part of the central auditory system. Now, when we think of the peripheral auditory system, generally it's anything that we have 2 of. We have 2 auricles, 2 of these, 2 outer ears. We have 2 eardrums, 2 sets of ossicles. We have 2 cochleas. And we do indeed have 2 cranial nerve number 8s, but physiologically, cranial nerve number 8 sort of is more in line with what's going on in the central auditory pathway. So even though you could make an argument that cranial nerve number 8 is part of the peripheral auditory system, you could also make argument that it's part of the central auditory system. For the purposes of this class, let's think of cranial nerve number 8 as being part of the peripheral auditory system, if only because it's easy to remember that the peripheral auditory system is anything that we have 2 of, 2 sides of your head, 2 ears, whereas we only have 1 brainstem and 1 brain. Okay, so central auditory pathway, brainstem, and brain. Now, we can further kind of demarcate the entire auditory system by the conductive mechanism, which is the outer and middle ear, and the sensory neural mechanism, which is the inner ear, cranial nerve number 8, and the central auditory pathway, okay? Conductive just has to do with sending the sound wave energy, sending those vibrations deeper into the auditory system. This part here is really just machinery, okay? This part here, the conductive hearing mechanism, more often than not can be fixed by a medical doctor. Conductive pathologies, in other words, diseases of the conductive mechanism, generally, for the most part, can be resolved by a medical doctor, by an ear, nose, and throat specialist, specifically by an otologist, an ear specialist. Let's think of what some conductive pathologies would be. A middle ear infection, where the space behind the eardrum is filled up with fluid. Earwax, like a plug of earwax within the outer ear. Those are examples of conductive pathologies. The sensory neural mechanism, though, cochlea, and then the retrocochlear pathway, everything beyond the cochlea, they generally cannot be fixed by a doctor. More often than not, the sensory neural mechanism, when it is damaged because of noise exposure, because of aging, because of head trauma, because of some sort of virus, because of ototoxic medications, those types of hearing losses, sensory neural hearing losses, just have to be rehabilitated. So in age-related hearing loss, for example, can't be fixed by a medical doctor. The only thing you can do at that point is put a hearing aid on. Now, we can further break down the sensory neural mechanism. You see the word sensory neural, it's got two words, right? It's a compound word made up of sensory and neural. Sensory is the inner ear. Sensory meaning the organ of hearing, the cochlea. Neural is the nerve, cranial nerve number 8, brainstem and brain. Okay, so when you hear sensory neural, you know that if it's a sensory neural hearing loss, that it's either the cochlea, cranial nerve number 8, or the brainstem or brain. Now, we as audiologists, for more often than not, we don't really get into determining where the pathology is. That's something really an ear doctor would probably care more about. We just would say it's a sensory neural loss, meaning it's the cochlea or beyond, okay? So sensory is the cochlea, the inner ear. Neural, cranial nerve number 8, brainstem or brain. Now, last but not least, you can think of this designation, these breakdowns, also being a part of what's called auditory transduction, okay? Transduction, or a transducer. A transducer is just something that changes, sorry, people keep texting me. Transduction, transducing, is just when energy goes from one form to another. So in other words, the outer, middle, inner, and central auditory pathways change energy, transduce it throughout the various aspects of it, okay? Sound wave energy enters the pinna, what's called the auricle, and at that point, it's just air molecules going back and forth and back and forth and back and forth. That's acoustic energy. Those air molecules hit the eardrum in the middle ear, and it becomes mechanical energy. At that point, the eardrum and the 3 bones behind it are sort of like a piston working on a car, back and forth and back and forth, at the frequencies and intensities that match the sound wave energy coming in from the air molecules. So acoustic transduces into mechanical energy at the eardrum. The foot plate of the stapes, the final of the 3 bones in the middle ear, puts the fluids of the cochlea into motion. At that point, the energy transduces from mechanical to hydraulic energy, okay? Hydraulic just has to do with energy as it's transmitted through liquid, okay? The fluids of the cochlea send the membranes of the cochlea along the 2.5 turns of the spiral of the cochlea into motion, vibrating, like I said, at similar intensities and frequencies as they did coming in. And at that point, the hair cells within the cochlea, which we're going to get into more in a second, start to fire. There's an action potential that causes the hair cell to fire, sending electrical energy down a neuron that then comes and becomes a part of cranial nerve number 8 and then goes to the brainstem and brain. So auditory information comes into the pinna via acoustic energy, air molecules bouncing back and forth, hitting the eardrum, where the eardrum starts to vibrate, or it becomes mechanical energy. We are through the conductive hearing mechanism. The stapes foot plate sends the fluids of the cochlea and the membranes of the cochlea into vibration, which is where it becomes hydraulic energy. And then as the hair cells fire, sending electrical impulses down the length of the various neurons that kind of amass, sort of like tributaries coming into a river, the river being cranial nerve number 8, sending information to the brainstem and brain via cranial nerve number 8 is where it becomes electrical, okay? You have to have this down. If you don't understand everything that I just said, you need to watch this video again. You've got lots of other things at your disposal. You've got the textbook, you've got the notes, you've got the various aspects of this slideshow that we're going to go through in a second. You've got the whole internet at your disposal, but it's just important that you guys be sure you understand this, because this is sort of the fundamental, I guess, this is sort of audiology in a nutshell. Once you have a basic understanding of this, you have a basic understanding of the entire auditory system and how ear and hearing pathologies befall it and what you can do about it, okay? So, anatomy and physiology. Now, I know I went through very briefly about outer, middle, inner, and central. We're going to talk a little bit more detail about what those are. When it comes to the outer ear, we are talking about this. We are talking about the pinna. This hard cartilage here on the outside, this isn't the earlobe. You could call this part the earlobe, although more often than not, that's called just the lobule. But don't call this the earlobe. It's the pinna, P-I-N-N-A, or auricle, A-U-R-I-C-L-E. That and the ear canal, which we sometimes call the external auditory meatus, EAM, the ear canal, that makes up the outer ear. Just those two things, okay? So outer ear is comprised of the pinna and the external auditory meatus, the ear canal, okay? We visualize the external auditory meatus with the use of an otoscope, O-T-O-S-C-O-P-E. This picture says otoscopic evaluation, otoscopic being the adjective, but an otoscope is the noun for the device that you use to shine a light inside. The outer ear does a lot of important things. We don't have a lot of time to talk about what all of those things are, but kind of basically the outer ear does two main things. It provides a little bit of resonance. In the last lecture we talked about resonance, where air molecules inside one thing get set into vibration as a result of vibrations happening nearby. So hoo, we blow into the bottle. The air molecules within the ear canal, being already there, respond to energy vibrating in outside of it, going in. The air molecules that are already in there give us a little bit of peak of resonance at about 2,500, 2,700 hertz. We get a boost, we get some amplification as a result of the shape of the ear canal and the length of the ear canal. So we get a boost, the resonance of the ear canal. Sounds at high frequencies sound a little bit better, a little bit louder to us as a result of the resonant quality of the ear canal. The other thing that the outer ear does physiologically is it protects the more delicate structures of the middle and inner ear. Earwax, cerumen, C-E-R-U-M-E-N, that's just a fancy way of saying earwax. Earwax is what sort of protects that. It keeps the bugs out, it keeps the dirt out, it keeps germs out from getting into the eardrum, from messing up the function of the mechanical aspect of auditory transduction, okay? Now, we could have a whole lecture on earwax alone. Usually when I do this class live, we end up spending about an hour talking about earwax. Earwax is something, it's one of those things kind of like boogers and farts and stuff that people think are gross, but they still love to talk about. The best advice I can give about earwax is just to remember the ear is sort of a self-cleaning mechanism. There are little tiny receptors in there that the more you dig in your ear, the more your outer ear thinks it's under attack, and it's going to start to produce more wax. So, in other words, the more you dig in there, the more you're going to need to dig in there. There's some weird cultural things, about earwax where people sort of think it's like hygienic or it's kind of a problem. Or like, oh, gross, that's so gross. Like anytime I look into an older person's ear, they're really like humiliated, like, oh my God, my earwax, it's so bad, I'm so sorry. And I'm like, why are you sorry? That's normal. It's normal to have earwax. It's abnormal not to have any. Now, obviously, if there's earwax on the periphery that you can get out, get it out, because it's not really supposed to be hanging out there. But you don't want to dig into your ear canal, because as I said, your ear will think it's under attack and just produce more wax. So it's a self-defeating sort of thing to clean it, like playing pool. I tell some of my patients, you can clean your ear sort of like you're mixing brownies or making a cake, but don't clean it like you're playing pool, okay? Don't stick anything into the ear. Just go in and go right here, just on the periphery, in this little hole area called the concha, but don't go in like you're playing pool, okay? We could talk a lot more about that, as I said, but we're going to have to leave it at that. The middle ear. The middle ear is made up of the eardrum. It's made up of the space of air behind the eardrum, which is called the tympanum, T-Y-P-A-N-U-M. It's made up of the ossicles, the three bones, the malleus, the incus, and the stapes. And it's also made up of the Eustachian tube, okay? Now, there's other things in there. There's some ligaments. There's some, nerves, the chorda tympani, all that stuff that goes through there too. But I don't need you to know any of that. Just focus on the eardrum, the space of air, which is called the tympanum, the three ossicles, the malleus, incus, and the stapes, and then the Eustachian tube. The eardrum, as you guys know, is a translucent organ that when you shine a light on it, inside it, the otoscope. The left ear, you should see a little kind of cone of light at around 8 o'clock. And in the right ear, you should see a little bit of light at about 4 o'clock. That sometimes can help you tell which ear you're looking in, or look if you're looking at a picture of an ear, which ear you're talking about. You can sort of see in this picture very sort of lightly the handle of the malleus, what's called the manubrium of the malleus right there. The head of the malleus extends up here above the eardrum into what's called the attic of the tympanum. But remember that behind the eardrum is a space of air, the tympanum. I can't think of any other part of the human body where there's intentionally supposed to be air inside the body, right? Our bodies don't like air inside it, right? If you inject air into a person's bloodstream, right, it's supposed to kill them or something. I don't even know. But there's a reason why, we burp and we flatulate. It's to get rid of air out of our digestive alimentary canal, right? We don't like or want air inside of our body, and yet behind our eardrum we have a space of air. Now it's a very small space of air, but we need it to be air in order for the process of auditory transduction to happen. That mechanical aspect needs to be air behind there, and furthermore, it needs to be air that has equal pressure on either side of the eardrum. Now, let's think about this. We as human beings evolved as, from ancient man to where we are now, sort of with the idea that we sort of lived at the same sort of elevation, at the same sort of height above sea level. Ancient man didn't travel enough from where he or she lived to really have any need for pressure changes to make much of a difference on the system. But nowadays we go up on an elevator to the top of the New World Trade Center very rapidly, right? We get on a plane and suddenly we're 35,000 feet above sea level. Our middle ear system via the eustachian tube can't really keep up with those pressure changes. So we're on the ground where it's relatively high pressure, and then we go up in a plane where it's relatively low pressure. The space of air behind our eardrum still thinks we're on the ground. We go up in the air, and it isn't until we and pop open the eustachian tube, equalizing the pressure on either side of the eardrum, giving us sort of a relief from that pain or pressure that you might feel, right? It's the reason why babies cry on airplanes, because babies don't have the ability to force the eustachian tube open. The eustachian tube is a tube that connects the nasopharynx, so to the upper throat, and the ear. We need that eustachian tube to open up in order to not just equalize pressure, but also to provide a means or method for any of the gunk or slough that comes from the cells within the middle ear space to slough off and drain, okay? The middle ear space is not only aerated, it's not only an air-filled space, but the walls of the middle ear space of the tympanum are wet. They're what are called mucosa. Mucosa is any sort of tissue that's wet, like the part of my lips here, our sinuses. You guys understand what mucous membranes are. The middle ear has to be mucosal. It has to be wet. Now, if the eustachian tube gets blocked, as it often does when we're children, especially because the eustachian tube when we're children is sort of shaped like this. As we get older, it gets to be more shaped like this. But when we're children, shaped like this, there's nowhere for the gunk and the slough to go. That middle ear space fills up with fluid, and as you know, when fluid sits there without oxygenating it, it starts to get stinky. It starts to become infected. That's the nature of middle ear infections. It's the reason why children are much, much more prone to getting middle ear infections. Children nowadays, unfortunately, and this isn't a dig on parents, but children spend way too much time in their car seats and strollers like this. There was a time, and it's going to sound like I'm an old man, like back in my day, but when I was a kid, kids walked a lot. Kids don't really do that anymore. Everybody's too busy. Kids are spending way too much time like this. And if kids are already predisposed to having asthma or allergies or any kind of sinus problems at all, those eustachian tubes are going to get blocked, causing a mild to moderate conductive hearing loss. And in one of the very first lectures, we talked about how a child needs to be able to hear the sound, not just so they can hear speech sounds coming into them, but so that they can hear that when they are producing them, that they're producing them accurately. It's the reason why, if within your family you have some kids that started talking very, very late, they probably had ongoing what's called otitis media, where the middle ear space, the tympanum, filled up with fluid for lengths of time. The eustachian tube, once it opens up and the fluid drains, that relieves the fluid, but sometimes it just doesn't. It's the reason why sometimes kids that fall under that category have to have ear tubes put in to allow for the drainage to come this way, out their ear, instead of down the eustachian tube, okay? We're running out of time here, so I need to keep going. But the inner ear is the organs of balance, which we're not going to talk about. We just don't have the time. But also the cochlea. So we also have the semicircular canals in there, the utricle and the saccule. But when we're talking about the inner ear as it pertains to hearing, it's just the cochlea. Now, please, 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 it is the cochlea, C-O-C-H-L-E-A. I don't know what it is, but for some reason, many of my students think, I don't know if they think it's funny or they just aren't really paying attention. They call it the cochlear. Cochlear, when you put an R onto the word cochlea, that turns it into an adjective. So cochlear implant, cochlear hearing loss. But the noun is cochlea. If you put cochlear on a test, I will count it wrong. I'm sorry, I'm just done with it. To me, it's just people being sloppy. You need to understand that the noun is cochlea, C-O-C-H-L-E-A. If you call it the cochlear, I don't know what that is. It just makes you sound ignorant. So please, please, please call it the cochlea. But if you're using it as an adjective to describe something else, by all means call it the cochlear. But as a noun, as a self, as something standing off by itself, it's the cochlea. Okay? We don't have a ton of time to talk about the cochlea, but suffice it to say that's where it all gets really interesting. The cochlea is the organ of hearing. So if you get asked on a test, what is the organ of hearing? The answer is the cochlea. Now, we've had some students put the ear, which is technically correct, but cochlea is a better answer, okay? Within the cochlea, we have a bunch of tubes happening inside of bone. This is the bony labyrinth of the cochlea and then the organs of balance. The cochlea itself is this little spiral right here, this thing that looks like a cinnamon roll a little bit, or Princess Leia's hair buns, or snail, I guess maybe is a better metaphor. The 2.5 turns of the cochlea are where we hear, okay? So the fluids of the cochlea, this is the stapes footplate, goes right into here, which is called the oval window. The stapes footplate goes in and out with mechanical energy, causing the fluids of the cochlea to move, causing the membranes of the cochlea to move. And along the 2.5 turns of the cochlea, we have what's called tonotopic organization, okay? I'm going to find a picture here. But the 2.5 turns of the cochlea, each part of the cochlea is coded for a different frequency, okay? You can see that where the stapes footplate comes in is where high frequencies are coded. At the top of the cochlea, the apex of it, is where low frequencies are coded. Now, it's a little counterintuitive. One might think that high frequencies are coded at the top and low frequencies at the bottom. You know, we tend to think of things as going from low to high, or from left to right, or from small to big. This is an example where going from entrance to going from bottom to top, we go from high to low. But it also helps understand why, as we age, that we lose high-frequency hearing first. All sound wave energy enters the cochlea here, but will only cause vibratory energy at certain aspects of the membranes of the cochlea to occur where that frequency is coded. So going back to the tuning fork example that we had earlier, boom, let's say we've got a tuning fork at 4,000 hertz. Vibratory energy is going to go into the ear canal, cause the eardrum to vibrate at about 4,000 cycles per second. The ossicles, the stapes footplate, the fluids, the hydraulic energy will then cause the cochlea hair cells right here at about 4,000 hertz to start to fire, sending information to the brain. And just like we have tonotopic organization in the cochlea and the auditory cortices on both sides, mostly on the left side, but also on the right. We have information coded tonotopically going from low frequency to high frequency in the auditory cortex in the temporal lobe of the brain, okay? It's tonotopic, meaning frequency coded by place, okay? That's like an entire sort of semester of anatomy sort of broken down for you very, very rapidly. But beyond the cochlea, after cochlear hair cells fire, we go up the brain stem and brain via a pathway that starts with the cochlear nucleus, the lateral lemniscus, the inferior colliculus, the medial geniculate body, and then going to the auditory cortex, okay? You don't need to know any of this stuff. Just the auditory pathway going through the brainstem and brain is fine. But one thing I do want you to know, because this is very important, most information that enters this ear crosses over and is read and understood in this auditory cortex. Most information that comes in this ear crosses over somewhere in the brainstem and is coded over here in this hemisphere, in this auditory cortex. It's the reason why we as human beings do very well at localizing sound, because it's a very complex sort of structure. Sound coming in here, sound coming in here, but sound crossing over at various places, what's called decussating, at various places along the brainstem, and then being read on the opposite part, okay? That's anatomy and physiology of the auditory system in about 26 minutes. Thank you for hanging in there. And I guess that's it. As always, email me at pcadamson@yahoo.com with questions. Thanks, class.